All right, the first type of proof I want to talk about is called a direct proof. And so we'll talk about a direct proof. And this specifically is a proof type where you have something of the form P implies Q. A direct proof, what we're going to do is we're going to assume P is true, and then we're going to deduce Q. And I want to remind you that the truth table, if we have P and Q and P implies Q, the truth table will be very helpful here. So for the truth table, 1, 0, 1, 0, we had 1, 0, 1, 1. If we want to prove that this statement is true, we want to somehow end up in one of those three cases. And now notice that these last two cases are always going to be true if the statement is false. So we don't have to do anything. Okay, there's no work to do. What we're going to do is we're going to start by assuming that P is true. So we're going to assume that we're in one of the first two cases. And then from there, we'll deduce that Q is true. And if that's the case, then we've deduced that P implies Q is true. Okay, so that's the idea. That's how our proof is going to work. I think the first kind of example that we can get into with a direct proof is going to involve the idea of evenness and oddness. And this is something that is probably familiar with, it's probably familiar to you already, but just to be 100% clear about what we mean by even and odd, we say that an integer, say x, is even if there exists an integer k. So if there exists an integer k such that x is equal to 2k. And likewise, an integer x is odd if there exists an integer k such that x is equal to 2k plus 1. And so to be even means that you can write x as 2 times an integer. To be odd means that you can write x as 2 times an integer plus 1. So of course, just to do a silly example, 7 is odd because you can write it as 2 times 3 plus 1. 8 is even because you can write it as 2 times 4. 9 you can write as 2 times 9 halves, but that's cheating because we specifically want this value to be an integer. So that kind of idea is out. Okay. Otherwise, I mean, pi is 2 times pi over 2. Also not useful because pi over 2 is not an integer. So we can't talk anything about evenness or oddness of non-integers in any meaningful way. So let's do this. Let's prove that if x is even and if y is odd, so x and y are integers, so if x is even and if y is odd, then x plus y is odd. Okay, so let's prove that. Let's prove that if x is even and y is odd, then x plus y is odd. Of course, we'll do a direct proof. Our direct proof, I just want to kind of think about the anatomy of this proof just for a second. So let's break it down. We're looking at the statement x is even and y is odd. And that implies, this is the logical implies, not the word, but this implies that x plus y is odd. So this is a statement of the form P implies Q, where P is our statement that x is even and y is odd. Q is our statement that x plus y is odd. So our hypothesis, if we're going to do a direct proof, we're going to start by assuming that our hypothesis is true. In other words, we're going to assume that x is even and y is odd. Okay, and then from that we want to deduce somehow that x plus y is odd. Well, to be even means that there exists an integer k such that x is equal to 2k. And likewise, if y is odd, then there exists an integer, we can't use k anymore because k is taken in the proof. Notice that if I say that y is equal to 2k plus 1, then I'm assuming ahead of time that y is equal to x plus 1, which it may not need to be the case. But if y is odd, then there exists an integer L such that, or so that y is equal to 2L plus 1. And now the thing that we want to say something about is x plus y. So x plus y is equal to 2k plus 2L plus 1. But that's going to be odd because you can write it as 2 times an integer. In this case, the integer is k plus L plus 1. So x plus y is odd. Okay, so there's our proof. And again, when we do these proofs, I will try very hard to start, and I've already missed it, but I want to start by writing proof, and then I'm going to end by writing this little box here. Okay, so that signifies that it's the end of our proof. So this is an example of a direct proof.